Our next application of Newton's second law of F net equals ma is something that I call connected objects. We will have another application after this, but sort of backtracking, you should be okay after grade 11 with vertical stuff like elevator problems, finding the normal of something accelerating up or down. You should be okay with horizontal ones. You should be okay with horizontal ones when we add coefficients of friction. You should be okay with horizontal situations when the applied force is on a funny angle. And after yesterday's new stuff or last lesson's new stuff, you should be okay using F net equals ma when objects are accelerating up or down an incline. The next new piece, and when you get going with this will be cool because it'll backtrack and we'll add inclines to this, we'll add coefficients of friction. But our next piece, connected objects, are kind of like that little graphic that I've shown here. If we were in a classroom situation, I would doodle this graphic on the board and I would just throw to the class just an open question. If this thing were free to move, the one that I labeled as capital M, is capital M going to accelerate downward at 9.8? And then I just let you think about it. If you're sitting by someone else in the classroom, I'd let you talk about it. But just look at that scenario without any real numbers. If we've got a mass on like a tabletop and then a string going over a pulley connected to a mass that's hanging, will that hanging mass, will it fall at 9.8? Think about it. Typically when I do it in class, if I gave you time to think about it, had to chat about it with a classmate, usually people get that, yeah, M would not fall at 9.8. If it does go down at 9.8, really that's saying it's in free fall. And it doesn't make sense for it to be in free fall because it's connected to that stupid little m, and that stupid little m is going to slow it down a little bit. So however you wrap your brain around it, that capital M is not going to free fall. It's not going to fall down at 9.8 meters per second squared. There's going to kind of be a little bit of tug of war. The capital M, it is going to go down. If it's going to move, it's going to move down. Maybe if there's a ton of friction, it wouldn't move, but we'll deal with that as we get to more tricky ones. Capital M is going to accelerate downward. It's just a question of how much it's going to accelerate. It won't be 9.8. 9.8 would be if it's free falling, but this stupid string that's tied to it, connected to stupid little m, that's going to slow it down a little bit. Solving a question like this one, there's more than one way to do it. Some of you might look at that simple connected objects that's on the screen there, and just your brain can kind of see it, and you'll say, okay, there's a force of mg, but it's acting on two masses, so we've got like F net equals ma turns into mg equals m plus m times a, or something like that. If you can see that, that's great. But when I start giving you more complicated ones, I don't think you'll see it as easily. So I'm going to show you a way. I'm going to come up with like an algorithm of sorts, a process that will work for all of these questions, no matter how complicated they get. If you do see a simpler way, you can try it. But sometimes those simple ways, I would suggest you work through the algorithm so that when you get to the more complicated ones, you have some tools to use to solve more complicated ones. So here's my algorithm. We're going to have two objects. Sometimes if I'm really cranky, I'll give you three objects. But however many objects we've got, draw a free body diagram for each of them. Then you're going to focus on one object at a time and work through those free body diagrams as far as you can. From what we learned when we went through inclines and when we talked about an applied force on an angle, there's none in this first example that's on the page, but if there are angles or inclines, then you'll have to do your component work. Push them as far as you can. There is a connecting force, that connects the one object to the other object. That connecting force is always going to be equal and opposite. So here, I'm going to do a little bit of doodling. When you eventually watch this video down here, it'll be in there as well, but just so you have it twice. Let's say I drew the free body diagram of this lowercase letter m. It's kind of what I would call a boring case. We got gravity pulling it down. The normal reacts and lifts it up. There's nothing on a funny angle. And it doesn't say anything about little m trampolining into the sky. So before I go any farther, well, at any point I could write down that I recognize that it's boring, that normal equals fg, so the normal is equal to mg. In the horizontal, we got a tug of war. There's a string pulling it forward. And, oops, if there is any friction, there'd be friction backwards. Oop, there is friction. Sorry, didn't proofread my own question. There is friction, so classic tug of war like we saw in grade 11, we have a friction force pulling it backward. So when we set up F net equals ma, in the horizontal I got a tug of war. The forward force is going to win, it's bigger, so I'm going to say Ft is a positive minus Ff equals ma. That's what I get that's what I get when I look at little m. We could push it a little bit farther. We know that Ff equals mu times the normal. We know that turns into mu mg. But for this quick little video, that's as far as I'm going to go. You can go farther and get an equation as simplified as you can. Call that equation number 1. Okay, you're going to squish it over here, but if I do a free body diagram on capital M, it's got two forces acting on it. Gravity's pulling capital M down, and then the stupid rope is slowing it down and pulling it back up. What I meant in this part, pulleys aren't going to add any force, and ropes on their own don't add any force, or strings don't add any force. So whatever force is accelerating the one block forward, so in this case I called it tension, it was a positive force on little m. That exact same force is a slowing force on the other object. So it's equal but opposite. It's accelerating little m forward, but slowing big M down. So when I set up my F net equals ma on the hanging mass, it's accelerating downward, so I'm going to call down positive. Tension is slowing it down, so tension is going to be a negative, equals, and it's capital M, so I'm going to put capital M in there. So what I want you to notice, if you follow this sort of algorithm, you're always going to get this sort of setup. The connecting force, which I'm usually going to call tension because there's strings connecting them, is going to be positive on one object. It's going to be the exact same tension, but negative on the other object. The last little piece is pulleys don't really push one harder than the other or allow one to move differently than the other. If the string or whatever's connecting them was stretchy, then it would get a little bit weirder, but we'll save that for university. The other thing is, because there's no stretchiness or weirdness, they're accelerating at the same rate. So in a connected objects, if we have two objects that are connected to each other, we're going to end up with two equations. One equation, sorry, this is getting a little bit messy. One equation has our connecting force as a positive, and it's equal to m times a. Our other equation has the connecting force as a negative, and it's equal to m times a. They've got common unknowns. We don't know Ft, we don't know a. So really what this turns into is a system of equations. We'll rearrange one and sub it into two, where there's a really neat trick. You'll see it when you look at the solution to example 1. If we just line up these equations and add the two equations, the negative Ft in the second equation plus the positive Ft in the first equation cancels out, so we can eliminate Ft simply by adding the equations. I think at this point that's a good place for me to pause, and you should work through or watch the solution for example 1 and see if you can work through example 2 and then watch the solution to see if you can get it. Example 2, you'll notice I added a little wrinkle. The applied force is on a funny angle, so that'll affect the normal force on the first one, all that good stuff that we did when we did applied force on an angle. But you'll have a Ft backwards that we don't really know what that force is, will be one of our unknowns, but it'll be the same Ft forward on the other object. And if we look ahead to example 4, a really cool example, the incline stuff that you learned in last lesson, that'll come up again in our connected object stuff. So connected objects are really a cool application. Physics teachers, well, we all do, I do. What I like about connected objects is an understanding of connected objects also means a built-in understanding of these other things we've been talking about, applied forces on an angle and inclined planes. All right, that's enough talking about this topic for me for now. Work through the examples, try them, then watch the solutions. There's a worksheet there, there's a check-in there. Um, Email at any time if you got any questions. Good luck with this one. Next lesson, we're going to not ramp it up. We're going to bump up the difficulty a little bit again with something new. We'll start talking about circular motion. So take your time, make sure you're comfortable with this. Email if you got any help, and then we'll move on in the next lesson.